confidential computing. It's a bit of a mixture between high-level overview and a few technical details due to the brevity of time. So for those that are not aware in the beginning, they should take something from it, as well as those that know a little bit more about confidential computing and Intel SGX. So when you look at typical data processing challenges and look at the sectors here on the left-hand side and the business and in their business environments, as well as the technical use cases on the right-hand side, they have something in common. And what they have in common is that they're both centered around handling specifically sensitive data, sometimes personal data as well. And for that, they typically, as you all well know, they employ all sorts of controls in the process of doing so. Various forms of isolation, integrity measures, access controls, etc., etc. The most common technical tool employed, however, in this is encryption applied to the data itself. But there's a little bit of a catch when you look at encryption and how it's being used. Up to very recently, we could only encrypt data while it was stored, meaning data at rest, as it's called, or while it was being transferred, so data in transit, as the name implies. But data processing inside a computer, inside a server, required code and data to be in clear text, rendering the server's internal architecture very critical for end-to-end data protection. Recently, though, the IT industry has started to close this last mile challenge for data. Data in use protection via encryption has become available and usable. There are two main methods on offer. One is homomorphic encryption, which is a way of processing encrypted data directly, with the result also staying encrypted. This is very mathematically heavy and therefore also very processing intensive. It's not yet generally a production-ready solution outside of some very niche cases. And then there's confidential computing, which basically means employing trusted execution environments that are opaque and encrypted when viewed from the outside, while code running inside the trusted execution environment, or TEE, can access the data inside the TEE in clear text. Basically an encryption wall around your execution. So where does this model help? With such data and use protections, we can now unlock scenarios that have been very difficult to implement without this protection. With confidential computing, the data is now protected against also malicious administrators, hackers who may breach the multi-tenant boundaries, and access from even the cloud provider itself. Organizations can also protect their data from themselves, because you may have come across the cases where certain organizations see the data they hold on customers more as a liability and not an asset. I know specifically of a few medical companies looking at it like that. And they want to build services where only algorithms can use the data that have been pre-approved, and the data may be too sensitive even for employees of their own company. Finally, an exciting scenario, I think, is which we're seeing with confidential computing. It is purely in that sense only possible that way, is enabling organizations to do multi-party analytics or multi-party computations and machine learning together. Multiple parties can bring their data together. They don't need to trust each other necessarily. They don't need to expose the data to each other, but they can merge the data inside a trusted execution environment. Where none of the parties can actually see the full data set, but run a computation on that shared data and profit basically from the results provided to all authorized parties. So that example you see often enough in, for example, federated learning use cases in medical or banking environments. So one of the first widely available confidential computing technologies in the cloud market was Intel's SGX. It still is. It was first introduced on client platforms, so mobile and desktop, with fairly limited capabilities, and has now grown to be a cloud and data center only technology. So the client technology has been end-of-lifed. It is in production across many sensitive data use cases that I've already mentioned, healthcare and life sciences, financial services industry, and even in retail, and has become a recognized option to implement privacy-preserving applications. That's the key word here. It's available on the current main server product, that's the Xeon of the 3rd generation called Ice Lake, and offers the capability of up to 1 terabyte of protected memory for large enclaves. So basically you can put fairly big applications inside such TEE. Each of those TEEs will have its own individual keys managed by the SGX business logic, and that is out of reach for any privileged access, even on system software. It's fully enabled by now in kernel.org in Linux since 5.13, which means both the bare metal usage of SGX and the KVM usage. And it features, quite importantly, extensive remote attestation capabilities, ensuring that only signed off and validated code will be run on a properly patched SGX system and in such enclaves. With no platform and firmware totally guaranteed to be secure, however, SGX also features some ways to gracefully handle firmware and microcode updates should these be necessary. So there's a bit of a security lifecycle management included in the design of SGX. So to compare SGX with other ways to encrypt memory while processing, have a look at this diagram and let's go through the layers here. Without any in-use protections ongoing, it's clear that you will have to critically trust every single component and actor involved in this platform, or with this platform, for a good security posture. Encrypting all memory traffic without distinguishing between the workloads and tenants with a single randomly generated key, which is the second line here, will at least stave off physical attacks on the memory bus, but it basically changes nothing with regards to software stack security. Trust domain extensions, that's the technology on the third line that's coming in future Intel processors, combines the attestation capabilities that I've mentioned for SGX together with hosting a full virtual machine inside an enclave. That's clearly convenient, but it keeps the full VM stack inside the trust boundary and therefore has a still fairly sizable attack surface. Still have to manage manage well, basically, all of the privileged access to guest operating systems, to the VM administration, etc. Lastly, with SGX being a process-oriented TEE, that means there's no operating system, no virtual machine inside the enclave. It offers the smallest possible trust boundary, making it easier to keep attack surfaces small and focus development work on the security critical parts of the application. So in that respect, it's kind of a shrink-wrapped trust boundary around your most critical parts. So with no operating system inside an SGX enclave, how do you actually write applications for it? The basic and original way was and is to use an SDK. There's the open source Intel SGX SDK, where you program directly towards the enclave abstraction and manage manually all of the OS operating system needs of an application running inside an enclave. This offers greatest control about attack surface and performance, but is obviously more work than just lifting and shifting an existing application. So that's the idea on the right-hand side. And that's a more recent ecosystem trend where we have more and more lift and shift runtimes for SGX, both in open source and commercial. These are often library operating systems. That means they operate via relinking an application so that the operating system calls of an application will be handled by a library inside the enclave when possible, and will negotiate the use of proper host OS services when required. So breaking out of the enclave on demand and handling that, including the keeping the secret outside of the enclave as well. So finally, if you want to make SGX available on any bare metal infrastructure or in containers or in virtual machines, you can start simply by enabling it in the BIOS of capable servers. If you have one that's properly equipped, using latest generation official kernel will make the appropriate CPU flags and dev SGX advices appear. That's as simple as that. With KVM enabled and using QEMU from 6.2 on, you will see the same appear in virtual machines, while the latest libvirt, I think that's due to be released, will make SGX options consistently available for SGX management as well. If you want to create Kubernetes clusters with SGX nodes, there's also an SGX device plugin. There's also an OKD operator available to properly find and schedule to nodes with these capabilities. And then finally, there's as a cloud service infrastructure, you need also an efficient way to offer remote attestation capabilities. The prime way to do so is Intel's data center attestation primitives, open source components that can serve as the building blocks of such a service. So that's in a nutshell, and in a very short time, SGX, where we are standing today in terms of enablement. We're doing the same with regards to SCS at the moment. We're collaborating with Christian and Jens on making sure that what's been already upstreamed into OpenStack proper will also land properly in SCS. That's at least the idea we've started to engage on. So to summarize, confidential computing improves end-to-end data security by introducing this in-use data protection via encryption. And that is, in some cases, critical for new and improved solutions, business solutions for handling sensitive data in sensitive verticals. The Intel SGX technology is a Markus-established confidential computing way of achieving a very, very small trust boundary. It comes with attestation capabilities and has built-in management for these security patches that eventually will occur in a real-life environment. Intel SGX is available in mainstream open source software and, of course, also in commercial system software today. So thanks. I think we have very few 1-2 minutes for questions if there are any. So please ask if you have them.
Well, let me first say thank you, Markus. I have to admit I'm impressed by how much